Hello everyone. Welcome to today's presentation. I'm excited to have you here. Today, we'll be diving into Kotlin Suspend functions, interview questions, and detailed answers. On this first slide, you'll see the title and subtitle. It's all about exploring suspend functions in Kotlin and preparing you for interview success. We'll briefly cover common questions and provide clear, detailed answers to help you understand this important topic. Let's get started. Let's talk about why enums can't handle this kind of flexibility. When we look at the example with the sealed class UI state, we see that it can represent different states like loading, success, and error, each holding different data or no data at all. This flexibility is something enums simply can't provide, because enums are limited to fixed constants without the ability to hold varying data or states. Flexible types, like in this example, can hold different data types and allow multiple instances, giving us the versatility we need. On the other hand, sealed classes are designed to have a fixed set of subclasses, which makes them more powerful for modeling complex state hierarchies. Now, why do we prefer sealed classes over enums? One key reason is that sealed classes enable exhaustive when expressions. This means the compiler can check if we've handled all possible subclasses, making our code safer and more predictable. A sealed class is essentially a restricted class hierarchy, where all subclasses are known at compile time. This constraint helps us write more robust code because we know exactly what subclasses exist, and we can handle each case explicitly. So, in summary, sealed classes give us a way to model complex, flexible states with known subclasses, making our code safer and more expressive than enums, which are limited to fixed constants. So, when all subclasses are properly covered, there's no need to add an else branch in our when expression. For example, in Kotlin, you might see a function like this, handle, which takes a result object. Inside, we use when to check if the result is a success or an error. If it's success, we access the data. If it's error, we handle the message. Kotlin's compiler ensures that this when statement is exhaustive when working with sealed classes. Now, you might wonder how exactly does when work with sealed classes? Well, it simplifies domain modeling by making our code more explicit and clear. Since sealed classes restrict the hierarchy to a known set of subclasses, the compiler can verify that we've handled all possible cases. This leads to exhaustive handling, meaning we don't have to worry about missing any scenarios. Moreover, it boosts type safety because the compiler knows exactly what types we're dealing with in each branch. This approach is particularly useful for managing UI states, network results, navigation events, and API responses. Basically, any situation where you have a limited set of possible outcomes. Sealed classes are excellent for modeling restricted hierarchies because they clearly define the possible states or types, making our code more predictable and easier to maintain. So, in essence, they solve the problem of handling multiple related types in a safe and organized way, especially when working with complex domain logic. All right, let's talk about subclasses and constructors. When working with sealed classes, it's important to remember that subclasses must call the constructor of the sealed class. This is a key point because it ensures that the initialization process is properly enforced. For example, if we have a sealed class like API response with a constructor that takes a code, any subclass needs to call that constructor explicitly. Now, you might be wondering, can a sealed class have constructors? The answer is yes. And this restriction actually enables the compiler to perform exhaustiveness checking. That means the compiler can tell if you've covered all possible subclasses, which helps prevent bugs. There are some conditions around where the subclasses can be declared, depending on the version of Kotlin you're using. In newer versions, subclasses can be in the same package and module. In older versions, they need to be in the same file. So the key takeaway here is that all direct subclasses of a sealed class must be declared in the same file, or in the same package and module if you're using a newer version. This setup is what makes sealed classes so powerful. They provide a clear, controlled hierarchy that the compiler can understand fully. This is essential for writing safe, predictable code, especially when dealing with complex type hierarchies. Alright, let's look at this example. Sealed class ASO, we have val equals A, and there's a big red cross next to it. The key point here is that no, you can't just instantiate a sealed class directly like that. By default, sealed classes are abstract, which means they are meant to be extended, not instantiated on their own. This is a core concept because sealed classes are designed to restrict inheritance within a specific scope, usually to define a closed set of subclasses. So, trying to create an instance of a sealed class directly will result in a compile time error. This ties into our overall theme of understanding class design and access control in Kotlin. Knowing when and how you can instantiate classes is fundamental. Let's talk about using sealed interfaces for behavior modeling. Sealed interfaces in Kotlin allow us to define a restricted set of implementations, which makes our code more controlled and predictable. Unlike regular interfaces, they support multiple inheritance, so a class can implement multiple sealed interfaces if needed. Now, remember that classes in Kotlin support constructors and maintain state, which is crucial for modeling real-world entities effectively. The difference between sealed interfaces and sealed classes is quite significant. Sealed interfaces, like sealed classes, enable controlled abstraction, but with some flexibility. For example, sealed interfaces are great for defining a set of behaviors that subclasses can implement, and this makes handling exhaustive checks in one expressions easier. On the other hand, sealed classes are more about creating a restricted hierarchy of classes. They enforce that all subclasses are known at compile time, which helps ensure completeness in when statements, making your code safer. It's also important to distinguish between sealed and open hierarchies. Sealed hierarchies are closed, meaning no new subclasses can be added outside the sealed class or interface declaration, whereas open hierarchies allow subclasses anywhere in the codebase. Finally, comparing sealed classes to abstract classes and sealed interfaces, the key takeaway is that sealed classes provide a controlled hierarchy with a fixed set of subclasses, useful for representing algebraic data types. Abstract classes, however, are more flexible and open-ended, allowing inheritance anywhere. Sealed interfaces combine some benefits of interfaces and sealed classes, controlled, predictable hierarchy with multiple inheritance support. Connecting this to our overall theme, understanding when to use sealed interfaces versus sealed classes or abstract classes helps us design safer, more predictable, and more maintainable code structures in Kotlin. Let's talk about how sealed classes are useful for scoping domain models. They help us define a restricted set of subclasses, which makes our code more predictable and easier to manage. Now, a common question is, can sealed classes be nested inside other classes? The answer is yes. You can nest a sealed class within another class, like in this example with outer and inner. This is particularly handy when you want to encapsulate related logic tightly together. Moving on, nested sealed classes are frequently used in Android development. For example, the network state sealed class here illustrates different states a network request can be in, such as loading, success, or error. Notice how success carries data, while loading and error are objects. This pattern makes handling different states straightforward and type-safe. So to sum up, sealed classes can contain objects and be nested, providing a flexible way to model complex states or hierarchies, especially in large apps or domain models. This approach keeps our code clean, predictable, and aligned with the overall goal of writing safer, more maintainable code. Alright, so when we're working with generics in clean architecture, making our results flexible and type-safe is really important. That's where converting result string into result any comes into play. It allows us to handle different types more generically. Now, to support this flexibility, we use the out keyword in Kotlin, making T covariant. This means our result class can produce T values but not consume them, which maintains type safety. So what exactly is out variance? Let's look at the sealed class example. Here, the result class is sealed and has an out T type parameter. This allows us to treat a result string as a result any, which is super useful when dealing with API results that could be of various types. This pattern, using sealed classes with data classes, is very common, especially for modeling typed API responses. You can see how the sealed class provides a controlled hierarchy, and the data classes hold the actual data or exceptions. By combining this with generics and variants, we create a flexible, type-safe way to handle different result types across our app. So, in summary, sealed classes with data classes and generics give us a powerful pattern for modeling API results that are both type-safe and adaptable, fitting perfectly into clean architecture principles. Let's talk about Moshi, JSON, and Kotlin's serialization. When it comes to polymorphic serialization, you do need to set it up properly. It's not automatic. You have to configure it to handle different subclasses correctly. Now, can sealed classes be used in serialization? Absolutely, yes. They are actually quite useful, especially for implementing factory patterns where you have a fixed set of subclasses. For example, consider a sealed class response with different subclasses like success or error. You can define a companion object inside the sealed class, which provides factory methods like success, to create instances easily. This brings us to the question, can sealed classes have companion objects? The answer is yes, they can. And this is really useful because it allows you to add helper functions or factory methods directly within the sealed class itself. When we talk about serialization and companion objects, it's important to remember that companion objects can help manage serialization logic, especially when you need custom behavior or registration of subclasses in polymorphic serialization. So, in summary, sealed classes, combined with companion objects, give you a powerful pattern for managing complex data models cleanly and effectively within your serialization strategies. One of the huge advantages of using sealed classes in large-scale systems is that they help prevent runtime bugs. Because the compiler enforces updates across all when expressions, it ensures that every possible subclass is handled explicitly. This makes your code safer and more predictable. Now, what happens if you decide to add a new subclass, like a new state to your UI state sealed class? Well, the compiler will alert you to all the places where this new subclass needs to be addressed, forcing you to update your logic accordingly. For example, if you add a new subclass, say, a loading state, the compiler will remind you to handle this new case wherever your when expressions are used. This is especially useful in complex projects, where missing a new subclass can lead to bugs that are hard to trace. In the context of Jetpack Compose and coroutine flow state handling, these sealed classes are heavily used for managing UI states, navigation events, and API response wrappers. They provide a clear, type-safe way to represent different states your app can be in. This approach is very relevant for real-world Android development, whether you're managing UI states in MVVM architecture, handling navigation events, or wrapping API responses. And when you add new subclasses, the compiler's enforcement ensures your code stays robust and up-to-date, reducing bugs and maintenance effort overall. Now, let's talk about how sealed classes help us avoid memory overhead. Unlike traditional class hierarchies, sealed classes restrict the inheritance to a known set of subclasses, which makes it easier for the compiler to optimize memory usage. In this example, you can see a sealed class called authState. It has two singleton objects, logged out and logged in. These are single-instance states, which means we don't create multiple copies of them, saving memory and simplifying state management. So, what exactly is the sealed object pattern? It's a way to model states or concepts that have a limited, predefined set of options. Sealed classes are particularly powerful for domain modeling because they let us have multiple instance types, each with different data structures, all within a controlled hierarchy. For instance, each constant within a sealed class can have its own data shape, making it flexible for complex state representations. But it's important to note what sealed classes cannot do, like enums. Enums, for example, can have associated properties, but they are limited to a fixed set of constants. They're great for simple, fixed options, but fall short when you need more complex data structures or multiple instance types. When comparing sealed classes to enums with associated data, the key difference is that sealed classes give us more flexibility and better control over type hierarchies. They also work well with the sealed object pattern, where singleton instances represent shared states efficiently. In summary, sealed classes and the sealed object pattern provide a powerful way to model complex domain states with minimal memory overhead, outperforming enums in scenarios where data shapes and multiple instance types are necessary.